Today we will talk about polar coordinates. And first, why do we need polar coordinates? Polar coordinates. We were so happy with our x and y coordinate system. I have x, I have y, and my object is moving along some trajectory. We lived in two-dimensional world so far, and we described motion of this object in terms of vector r that had x and y component. This will be rx, this will be ry, rx, and ry. We also had unit vectors I and j. Unit vector I, by definition, has magnitude 1 and is always along x. Unit vector j, by definition, has magnitude 1 and is along y. And we had our r, vector r, the position of any object. We wrote it as rx unit vector I plus ry unit vector j. Or instead of writing rx, we used x for rx, so it was xi plus yj. I made a mistake. This should not be here. Yj. All right, but now imagine that I have a slightly different problem than one that we talked before. Imagine that I have this eraser and I want to rotate this eraser. So let me try. I have this eraser and I need to spin it. I can spin it, I can spin it this way in vertical, or I can spin it in horizontal. I hope you can see me like this. Almost. You got the idea. So I'm spinning it. In other words, what I'm doing right now, let me draw it. I have an object that is attached. So this is our old x and y coordinate system. I have an object that is attached to the string, and this object is moving. It could be a circle, could be a not perfect circle. This object has m. This length of the string, let's call it L, length that is given. And this is top view. What I draw is top view, view from above. So basically what I'm doing something like this in horizontal. I'm spinning it. Okay. Imagine this nightmare. So this object is moving, and if we start describing it in terms of fixed unit vectors I and j, it would be nightmare. Because every time the object is rotating, which means theta changes, but I and j are fixed. So instead of doing that, and instead of going into all this complicated math, we will introduce polar coordinates that will allow us to solve these problems on rotational motion in a simple way. So to do that, I need to introduce what we will call polar coordinates, and those will be r and theta. So what I will do next, I will erase the information that we don't need anymore. So I will erase this rx, I will erase ry, and I will describe motion of the object along this trajectory. So that's how my object is moving. I will describe it in terms of r and theta. And to do that, I need now to introduce new unit vectors. And these unit vectors we will call IR and I theta. So I will have a unit vector along r. So this is just continuation of r. We will call it IR. This is unit vector. Magnitude is by definition 1, and the direction is along r. Is it a straight line? and I theta is perpendicular to IR. This is 90 degrees. The length should be the same. I need to fix it. The length should be the same because this is also unit vector, so the length is 1. This is IR, and this is I theta. This is my new unit vector. And next question is how to express R, which is the position of the object, how to express R, velocity of the object, and acceleration of the object in polar coordinates. Well, I remind you that I and J did not depend on time. But now with our IR and I theta, we have IR and I theta moving with our object. So this is IR, always out of the circle. This is I theta, perpendicular to IR, in the plane of the board. And they are moving as the object spins. So now IR and I theta depend on time. Why do I care that IR and I theta depend on time? Because I need to derive velocity. So let me first write R in terms of our new unit vector. R is magnitude of R, length of this vector, times unit vector, which is IR. Makes perfect sense. But now, when I need to differentiate, I need to write dr dt in order to find the velocity of the object. Look what I will have. I will have dr dt. Which rule of differentiation will I use? I will use product rule. So I differentiate dr dt, IR, plus R. And since IR now changes with time, I have to write dir dt. Again, magnitude stays the same, but direction changes. So this is my dr dt. This is my velocity, but I don't know what is dir dt. I need to figure it out. So what we will do next, our next step will be to find out what we need to do. We need to find what are the rules, what are the expressions that we will use for dir dt. That's what we need to figure out. And we also need to figure out di theta dt. In order to figure out what are the derivatives of these unit vectors IR and I theta, I will bring them to the origin. So I will redraw our coordinate system, x, y, and I will start my unit vector from the origin. This will be, let me do it in red to have more contrast. So this will be my IR. And I theta is perpendicular. Unit vector I theta is perpendicular. This is 90 degrees, and their length is the same. Those two are unit vectors. Length is 1. So this is I theta. And IR makes angle theta with horizontal. This angle is theta. Okay, so now I need to express IR and I theta in terms of our usual unit vectors I and J. Let's do it. So IR will go first. IR. What is IR? Length of IR is 1. The projection in X will give me cosine theta, 1 times cosine theta I, because it is x projection, plus y projection of IR, which length is 1, and then 1 sine theta j. Now, since length is 1, I will erase 1. We will not leave 1 here because we already understood. Okay, length is 1. I just erase it to have our expressions a little bit shorter and better organized. Now, what is I theta? What is projection of I theta in x? First, it is negative. So I put minus. Length is 1. Which function of angle theta should I use? Look at this. This is theta. This is 90 degrees. Then this angle is 90 minus theta, which means that this angle is theta. This angle is theta. So my x component of I theta is minus 1 times sine theta I. And y component of I theta is positive, so it is plus 1 cosine theta j. What I need to do next, I need to differentiate. I need to find dir dt. Which rule will I use? Well, I need to use product rule, and then I will also need to use chain rule, because now theta depends on time. Let's do it. So first of all, I differentiate this first guy, cosine theta. Derivative of cosine theta is minus sine theta. Then I use chain rule, d theta dt, and we don't forget I. Now, I use product rule, so I write plus cosine theta di dt. We are done with the first guy. What is the derivative of the second guy? I again use product rule. Derivative of sine theta is cosine theta. Chain rule gives me d theta dt times j, and then I use product rule. So plus sine theta dj dt. However, what is di dt? I is a unit vector with fixed direction, so di dt is 0. dj dt is 0. So these two guys are 0. What I will do now, I will erase these two guys. And I will just rewrite this one. So this guy is 0. We don't need it. We already understood that, yes, derivative of I is 0. This will be gone. And this guy will be gone. And what I will do next, I will move this one a little bit closer. So this will be cosine theta d theta dt j plus cosine theta d theta dt j. Now let's look at this. Can I factor out d theta dt? Yes. I factor out d theta dt. And if I do that, what will be in parentheses? I will have minus sine theta I plus cosine theta j. But what is minus sine theta I plus cosine theta j? This is I theta. So what I have in parentheses is I theta. Okay, we keep going, and it is equal d theta dt I theta. Now we know how to differentiate IR. We have dir dt equal to d theta dt I theta. Now we need to derive di theta dt. Let's do it. So I will start here. Di theta dt. di theta dt is equal to derivative of sine is cosine, so it is minus cosine theta, chain rule gives me d theta dt times I plus minus sine theta, derivative of I will give me 0. So we are done with the first guy. Plus, and actually it is minus because derivative of cosine is minus sine theta d theta dt j. Let's factor out d theta dt. And actually what I will do, I will factor out minus d theta dt. Minus d theta dt. What I will have in parentheses will be cosine theta I plus sine theta j Look at this. What is cosine theta I plus sine theta j? Cosine I plus sine theta j is IR. So, derivative di theta dt is equal to minus d theta dt and IR. Now we know how to differentiate I theta. Di theta dt is equal to minus d theta dt IR. So we now we know how to differentiate vectors IR and I theta, unit vectors IR and I theta. And in the next video, I will derive velocity and acceleration in polar coordinates.